Hello and welcome to another video lesson. This one is Unit 2. We're looking at Lesson 20 and we're talking about rational equations, and this is the first part of it. So we're going to also see more of this in our next lesson, Lesson 21. Rational equations just means we're taking something that is a rational function, something that we have with like division going on, just making stuff up here. And now we're going to start seeing an equation part of it. So this is either going to equal a number over here. So maybe it'll equal 12. Maybe it will also equal another polynomial or another rational. And so we're going to see that we have some equals signs here that's going to make this change here now. Okay, so we have seen some equations before, especially with fractions. We're going to see how we're going to start to solve these. So today is just our first one, to write and solve some rational equations. Let's see what we notice and wonder from our first part of Lesson 20. And it's asking us to look at denominators and solutions. So some things I might notice is that the first two have the same solutions. So both of these two are with a solution where x equals 2. And our second two are also sharing the same solution that x equals 1. So that's something to notice. I also notice that for each of these, for part A, they have the same denominator. So it asked me to look at denominators and solutions. I noticed something about the solutions. Now I'm noticing something about these denominators. When they're in fractions, they are the same denominator. And the next thing that I notice is between A and B, the numerator of the first in part A is also just all that's left in part B on the left side of the equal sign. And same thing with the numerator on the right side. It's all that's left on the right side of the equal sign. So they must be telling me something here. The idea that if I have two fractions that have the same denominator, then their numerators also have to be equal to each other. So it's a nice way we can get rid of fraction or start to reduce something. So maybe you would think of it like this, that if I told you 2x plus 1 over 7 equals 10 over 7. Let's not make that 10. Let's make that 11. You'll see why in a second. That if these two are equal to each other, if they're both over 7, I could multiply both sides by 7. This is a legal algebraic step. Those would cancel out, and now I have 2x plus 1 equals 11, all that's left there. So if I have the same denominator, if they're dividing by the same number, our numerators have to be the same. Good thing to notice here. So that's what they're saying here, that if we have the same denominator, we can multiply both sides by that denominator, or we could just kind of ignore those denominators because our numerators have to be equal to each other. So they're saying that over and over again. So that's kind of a nice thing to notice and wonder and to get us started here. So if we ever have a solution where our equation has the same denominator on both sides or the same numerator on both sides of an equal sign, then the other part of the fraction has to be the same. Has to be equal. And then we can solve. Let's see how this is going to start working with rationalizing the price of t-shirts. The school art club at a large high school is in charge of designing school t-shirts and getting them printed. A local business charges $35 to set up their t-shirt. This seems like a flat rate that everyone has to pay. And then $4.25 in materials per t-shirt to print. So the more t-shirts that they buy, the more of this $4.25 they're going to have for each t-shirt. So an equation to represent the average cost, C of X, where X equals the number of shirts, C equals the cost, now we want cost per t-shirt. This is a key part right here, per t-shirt. So we're going to think first about our total cost, and then we're going to divide that total cost by the number of t-shirts so that we can get this cost per shirt. So our equation that would have our total cost is $35 to set it up. I only have to pay that one time, but I do have to add on to this cost that $4.25 per shirt. $4.25 times X. And I'm going to divide all of this by X number of shirts because I'm looking for the cost per shirt. So this makes sense. They might be saying, well, hey, we need to figure out how much we need to charge each student if they're paying for their own shirts. We need to get the total cost of everything to order them all, divide by the number of shirts, so we know how much each student needs to pay for that shirt. So we can find the average cost per shirts for 25 and for 100 by plugging in those values here. So our cost for 25 shirts, I'm going to plug 25 into my equation. 35 plus 4.25 times 25, all divided by 25 equals, and here's where I'm turning to my calculator to do this math for me. In parentheses, because I've got a fraction, 35 plus 4.25 times 25. I'm actually going to just do my denominator first, or my numerator first, sorry, that's on top. There's my total cost, and I need to divide it by 25 to get my per shirt cost. So $5.65 if they order 25. Now if they order 100 shirts, let's see what that cost is going to look like. Still has that flat fee, $4.25, this time times 100 shirts, and we're going to divide it all by 100 to see what that cost is per shirt. 35 plus 4.25 times 100, divide it by the 100 shirts that we're buying, $4.60 a piece. So 25 shirts is going to cost each student $5.65. But if they can get 100 people to order shirts, they can get it cheaper priced for $60 per shirt. So that's kind of a nice way to start reducing prices, is that you have to sell more. The cheapest average cost the t-shirt will get. There's a couple ways we could do this. We could plug in some bigger and bigger numbers. We could do something like find C of 100,000 or 1,000,000 or 1,000,000,000 or something like that. We could see what that extreme is when we plug in a super large number. And it's looking like it's getting pretty darn close to $4.25 here, but there's always a little bit of extra, a little extra cost because of that $35 setup fee. But here's a better way to go about that. We've been looking in our last couple lessons about using that actual polynomial division to see how we can write this as a result and a remainder. So let's see what happens. I'm going to use that heart division going on there because I've got two like terms. I've got 35 divided by x, and I'm adding 4.25 to x divided by x. So I gave it a little bit of heart, a little bit of love. I think I've said that before, with a little heart shape here, and then I'm going to rip my fraction apart into two fractions. So remember, this is like opposite of adding like fractions. They have to have a common denominator before we could add them together. We're just going backwards here and splitting them back into two separate fractions with a common denominator. Now there's nothing I can simplify over here, but I can simplify this x right here because it's in the numerator multiplying and it's in the denominator dividing. So 35 over x plus $4.25. This tells me that horizontal asymptote. Remember that idea? We know we aren't going to have a price at all if we order 0 shirts, so x can't equal 0. There's going to be a vertical asymptote where x equals 0. That vertical asymptote shows up there. And then our horizontal asymptote is what's going on here, this $4.25. And so we know that this is looking like that, and as we order more and more t-shirts, that is our x, that's our input. Let's bring it all back to context. As we order more and more t-shirts, the price gets closer and closer to $4.25, but will never get lower than $4.25. So that is where my answer is, right here. The cheapest average cost it will ever get is $4.25 each, because that is our horizontal asymptote. And it is telling us the end behavior of our graph. That's our value that it gets closer to. As we buy more shirts, as x goes up. So we can see already at 25 shirts, it's down to $5.65. That's going to be somewhere, right about here, because it's above $4.25. It's here. As we order 100 shirts, we're looking here at about $4.60. But it keeps on going down, 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 and closer and closer and closer, but it will never cross $4.25. That's the minimum it'll ever get. So this horizontal asymptote really starts to tell us a lot. Being able to divide helps us out. And how many shirts should be printed to have an average cost of $5 or less per shirt? Let's go figure this part out. Here's where our rational equation is coming in. They want, let's see, we have a $35 setup fee plus $4.25 per shirt. And we divided it by x. That's our equation. But I'm also going to write it in this way: the 35 over x plus $4.25, because that's what we did after polynomial division. So I'm going to look at it in both of these ways to help you see which one's a little bit easier. This one we don't know how many shirts it is, but we know we want the total cost to be equal to $5. And we could say or less than, so less than or equal to $5. We have an equation now because I can think of this like an equal sign and solve what we're looking at. Now there's lots of different great first steps we could take. This one is going to be a little harder because my first step would probably be to multiply both sides by x, which I could do. It's actually not that bad of a first step. 4.25x, 5x, got rid of that denominator by multiplying both sides by the denominator. So I have 35 plus 4.25x is less than or equal to 5x. I'm going to combine like terms. I'm going to do opposite operations. I'm going to subtract 4.25x's from both sides. And then my last step would be to divide by 0.75, so I could figure out how many x's by themselves. Let's see, 35 divided by 0.75. Looks like 46.6 repeating, but I can't order a partial shirt, so we'd have to order 47 or more. So with our starting equation, we know what our end cost has to be. We can start to solve this out using algebraic skills. Now, if I used this one here, it's kind of that same idea because, you know, it's, yeah, actually this way it might even take us more steps. We would subtract 425 from both sides. 35 over x less than or equal to 0.75. See how we're seeing some of the same numbers show up? And now, to get rid of a fraction, I'm going to have to do the same thing I did up here. Multiply by the denominator. And then to get that x by itself, we're doing that same step we had to do up here, divide by 0.75. So I guess it's the same number of steps either way, and we're coming up with our same answer either way that we go about it. Now, you don't have to solve it both ways. I just did because I was curious about that, to show you both ways, whichever one works better for you. So we'd have to order 47 or more t-shirts to have a cost of $5 or less per shirt. So that's kind of a nice way for them to know that if they can at least get 47 people to sign up, $5 a person, everyone can kick in as they're ordering. Now, batting averages gets a little bit tricky. It's a little bit more complex of an idea because when we have batting averages, we are adding up our total of how many times they've been at bat and how many times they've had a hit out of those total. So Tyler's on a school baseball team. He has had 24 base hits out of 110 at-bats. So his current batting average, he has 24 out of 110. His current batting average is 0.218. Looks like that's repeating. So they would say that his batting average is 218. But this is what it means. It's 0.218, 24 out of 110. He wants to raise his batting average to 300. That's a pretty good goal for a baseball player. So we want that batting average to equal 300. How many of the next consecutive at-bats need to be base hits to raise his batting average to 300? Write and solve an equation using x for the number of consecutive base hits. So his number of base hits, this 24, is going to be, if he gets all of them consecutively, we're going to be adding all of those extra at-bats as more hits, more base hits going on. But it is also going to raise his total of 110 because every single one of those at-bats is a base hit. So we have to add x to both his number of at-bats and his number of base hits. And we want to see how many of these it's going to take to get this proportion up to 300. So our x is how many more base hits and at-bats that he needs to have. So to solve this, maybe you're going to think about this 300 as being 0.3 over 1. I haven't changed that value. It means the same thing. We're just dividing by 1. And I can cross multiply. Remember, we can do that over an equal sign, only over an equal sign. But we can cross multiply. I like to just think of it as, hey, I've got a denominator. I'm not a fan of fractions. I need to multiply by that denominator to get rid of that fraction. So if I multiply by the same thing I'm dividing by, those two will cancel out. So from here, I'm going to use distributive property or polynomial multiplication. 300.3 times 110 is 33 plus 0.3x. So I did distributive property over there. Now I'm going to start combining like terms. So I'm going to get my constants over on one side and all my x's over on the other side. I'm going to subtract this 24 from both sides. I'm going to do this one step at a time so I don't try to bite off more than I can chew. 33 minus 24. Let's see, that's 6, 7, 8, 9. 9 plus 0.3x equals x is all I have left over on the right hand side. Need to gather my x's together, so right now these are adding, so I need to subtract 0.3x minus 0.3x. 9 equals 0.7x. And dividing by 0.7 will get my x's by itself. 9 divided by 0.7. So 12.8. But again, he can't have a portion of an at-bat, so he needs to get 13 at-bats in a row. Consecutive base hits in order to raise his batting average to 300. Now I'm not going to worry about number 3. We can just cross that part off. It goes a little bit more thinking about his next. He gets no base hits for his next 3 at-bats. It would change our denominator here. So he'd have 24 out of 113. Because he has 3 base hits and none of them were or 3 at-bats, but none of them are base hits. And then we just need to keep on doing the same thing we did before. We're going to add a certain number of x's to both if he's still trying to get to 300. So you can work through that and solve it through, but really this is our big idea, that we can set up an equation and we can use our algebra skills to solve that equation. Let's take a quick breeze through our summary and see what we've got. Nice, they're doing a lot of the same steps we did here, multiplying both sides by denominators to get rid of fractions and solving through and then interpreting. Pretty awesome. All right. Thanks for watching this video.